So, the wave properties of matter. The last chapter discussed the particle nature of light. This chapter flips it, based on a fellow called Louis de Broglie. He basically thought if photons can act like particles, well, sort of by the symmetry of the universe, could it be that if a particle is small enough, it could act like a wave? And so he basically did some experiments, and a bunch of people did a lot of experiments, and with electrons and protons and neutrons and things like that, fast-moving tiny particles, to see do they have this sort of wave nature. Now, if I were to ask you, diffraction, what is diffraction an example of? What nature of light, for example? Yeah, diffraction is a wave nature of light, okay? So, would you expect an electron to diffract? Well, of course not. It's a piece of matter. It's like a little ball that we imagine. You throw it at something and it's just a ball, okay? And so, but of course, experiments showed that electrons and tiny particles like that do have a wave nature, but that wave nature is wrapped up in their size and their mass. So when they're small enough, their wave nature becomes pronounced enough that you can actually see it, all right? And so that's what they did. Basically, you can infer from the behavior of electrons, protons, and neutrons and small particles like that, that all matter has a wave nature. It's just that that wave nature is so small when it's talking about like a big object, like a person or a chair or a table. Like if you throw a chair through a door, you don't expect it to diffract around the door, right? Its wave nature is so tiny. And in other words, its lambda, its wavelength is so tiny compared to the width of the door. And of course, if you think about it a little bit more, you're like, could you get the door narrow enough to get the chair? Well, no, because the chair just wouldn't fit through the door. Its wave is still much too short. No matter how narrow you make the door, it'd be nonsense. You just get a door that your chair wouldn't go through. All right, so Louis de Broglie realized that particles do have a wave nature. So, and that's what this stuff right here basically says, right? So back in 1923, he speculated that if light waves could be like particles, then particles could be of matter should behave like waves, you know, if they're small enough. All right, so it's come along. De Broglie suggested that the wavelength of a particle of matter could be found by using the same relationship that applies to photons. So if you know the wavelength from the wave nature of a particle, then you could calculate its momentum. All right? So that was what he brought to the thing. And then because of that relationship, he came up with this, which is the de Broglie wavelength. Lambda equals h on momentum, which is the same as h over mv. And you can see, but because you're talking about electrons or protons or neutrons or things like that, the mass has a meaning because those objects have mass, and the velocity has a meaning as well. Obviously, the velocity is always going to be something less than c because you're talking about a bit of matter. All right? So there are not very many confusing things in this section, but there are a couple of things you do have to keep separated because there are some comparisons in this chapter done between, say, the momentum of a photon of light and the momentum of an electron. All right? So they're the only real comparisons that we make, and they're the only real areas that we can get sort of confused. All right? So if we move on to the next bit right here, if electrons can diffract because they're showing their wave nature. Now, notice in the de Broglie wavelength, obviously V can't be zero. So you have to be moving relative to another object to actually have a wave nature. All right? V obviously can't be zero. Mass obviously can't be zero because it's an object. It has mass. Yeah? We're saying that as the object, because it's an electron, say the electron is standing still relative to you, I guess, if you look at it that way, well, then it's not going to have a wave nature. The object has to be moving to have a wave nature at all, okay? But it is still an object, still has mass, all right? I don't know if that actually answered your question, but the key is that it needs to be moving relative to you for it to actually exhibit a wave nature. Okay? Now, if you look at this, is a nice famous photograph that we see a lot of. And this is two different diffraction patterns. All right? So what they've got here is they've taken a piece of metal, like foil, really thin, and they've fired a beam of electrons at the foil. Now, the foil is nice and thin, so it's got lots of spaces between the atoms in there. And on one side, a nice neat side, we have X-rays. Now, X-rays are light, okay? They are photons. That's one thing that sometimes people interchange when they're doing this. They start to imagine that, oh yeah, X-rays are particles. They're not. X-rays are photons. They're part of the electromagnetic spectrum. They are just light, okay? Just high energy light. Now, those photons move through, and if you were to fire this, these X-rays at the foil, they will go through, and because the arrangement of the foil, the spaces are all over the place, and the beam hits, when they diffract out in all directions, okay? So, creating these ring patterns, and these ring patterns interfere with each other, and you end up with areas where there are bright bands and dark bands. So this is like a diffraction pattern, or interference pattern, sorry, an interference pattern caused by diffraction, but of a beam of photons being fired through a foil, all right? Where the gaps are actually the atomic spacing between the atoms of the foil, and that's kind of why they're going out in all directions, all right? It's not like a single slit, double slit sort of thing, all right? So, on this side, you've got the experiment done with photons. On the left, what they've done is they've done the experiment again, but they've used electrons, not of the same energy, but of the same wavelength, okay? So, in other words, the same momentum. They've used photons of the same momentum, electrons of the same momentum as the photons that they used, all right? And of course, if they have the same wavelength, then they interfere in the same way. So the rings tend to match up when you get it right. So the interference pattern has the same regions of constructive and destructive interference, okay? So this picture, obviously, this is a composite of two photos, all right? The experiment being done twice, split down the middle to show the comparison, to show how the effect of the wave nature can be observed very much like, obviously, the wave nature of light as normal, okay? The energy radiated, E is proportional to the frequency F of the radiation. Now, this is something we already know. E equals HF, which is what we've been using in the photoelectric effect. So we know that the energy of a photon can be given if you know it's either its frequency or its wavelength, all right? So you've got E equals HF, which is also HC on lambda. Now, this is the next area where students can make like silly mistakes. And that is, throughout the chapter, you're asked to calculate the energy of the photon being used, or the energy of the electron being used. And often you'll be asked to do that using the wavelength of that object. Now, if you look at the formulas that you've got at your disposal, if I need to calculate the energy of an electron, all right, and I can see in the question, or I've worked it out, I know it's wavelength, and I, without enough care, apply this formula, E equals HC on lambda, why will I not get the right answer? It's not going at the speed of light. Any particle is limited from actually traveling at speed, which means you cannot use that formula to calculate the energy of an electron or a proton or anything like that, because the C doesn't apply. This is quite specifically for the energy of light, whether it's an X-ray or a gamma ray or whatever it is. It doesn't matter as long as you've got the lambda, the wavelength, and you know that it's light, which means it's traveling at C, all right, then that's when you use that formula, okay? Now, let's see photon let's see. The modern theory of light is a merging of the wave and particle models. Light is imagined to travel in a stream of packets or quanta of energy. The energy carried by each quantum is proportional to the frequency of light. You know all of this from the last chapter. Equals HF. Greater intensity of light has more photons, but each photon still has the same energy. Again, you should be well practiced in that already. Photons are neither particles nor waves. They have a set of properties that have some similarities to particles when traveling through a vacuum. All right, at this part of the course, we always watch the same video. We watch Dr. Quantum, and he explains the experiment that shows electrons causing, or the idea behind electrons causing interference patterns, okay? So, I love how they make it look really mysterious. How does the electron know it's being watched? How? Can anyone think how the electron would know it was being watched? Yeah.
Because you have to interact with it
to see it, exactly. You don't just look at it. I mean, yes, you can just look at it, but the reason that I can see this texture is because light is coming from somewhere, bouncing off it and going into my eye. I can't see it unless I touch it in some way. And that is what apparently destroys the probability function, that once you've observed it, to observe it, you had to have interacted with it. And then it's no longer probability. It becomes, no, you're there. And as soon as you look at the next one coming through, oh no, now you're here, right? Don't look. In other words, these effects could only really happen in the dark because you don't get this idea. You'd have to look it up what superposition is. Like superposition is when an object occupies multiple states all at the same time until an observer bounces something off it to see where it is. And then all of a sudden it's not in lots of places, it's here. Okay? And so it's there's a whole bunch of YouTube videos that help you understand sort of what's going on there, all right? But yeah, you take an object that's really, really small, you make it move very quickly, it will appear to be spread out over a large distance, area until you measure it. Okay, and so that was it's not actually that mysterious of like, oh, how does the electron know it's being watched? It's like, it doesn't. It's an electron. It doesn't know it. So when you're doing your questions, that you don't make these common mistakes, all right? So the de Broglie wavelength itself is lambda equals h Planck's constant over mv. Now this brings us to Planck's constant having two versions. Now momentum is pretty much an SI unit and doesn't really have an alternative unit, okay? Which means do not make the mistake of using h equals 4.14 when you're calculating the wavelength of an electron or a proton or a neutron or any particle like that. You must use 6.63 because it's a standard unit. It doesn't have another version, all right? So h in all of these cases is 6.63 times 10 to the negative 34 joule seconds, okay? So that's one little trap. Don't get sucked in and use the wrong one by accident, all right? Okay, now, if you're calculating the momentum, often these questions are about the comparisons, okay? The momentum of a photon or the momentum of an electron, okay? It's mostly electrons, but not always. If you're calculating the momentum, to calculate it for a photon, okay, you calculate it, momentum equals h on lambda. Again, it's momentum, so it's 6.63, all right? Or hf on c. And again, that's on the photon. That's why you can use c, because you know it's speed. It's given. It's constant. All right? The momentum of an electron follows the same sort of rules, except that you can use its wavelength. If you've calculated its wavelength based on its velocity, then you can use h on lambda to calculate the momentum of an electron. Okay? In other words, using its wavelength. And that was what De Broglie basically said, that, oh, we should be able to use that for both. Okay? Also, MV, it's mass velocity. Now, of course, in this level of physics, we don't worry about relativistic effects. If the electron is moving like close to the speed of light, we kind of ignore that, just to get our heads around this concept first. Later on, when
formulas not work because we're not doing that. Or do they not work when you
I think what if you're going to really high velocities, you'd have to just take the mass energy into account when you were actually doing calculations, I assume. But we've never had to do that in year 12, so I've never had to actually try that. So anyway, okay, so that's your momentum. Now, something that you can say is true, is that if they have the same lambdas, then they have the same momentum. Because you can see we use the same formula to calculate both, all right? And hence this leads us, same lambda, same momentum, okay? Now this leads us to the other thing that they constantly ask you when you're doing questions on this topic, okay? When we go to the energy, an electron and a photon with the same momentum do not have the same energy. They have different energies, okay? And of course, that's the question they ask over and over again to see if you know that, to demonstrate you know the difference, okay? That's the only real trap in these questions. They will force you to demonstrate that yes, their momentums are the same, but their energies are not. And that is just something that they harp on the whole time, okay? So to calculate the energy of a photon, so energy of a photon, E equals HF, which is the same as HC on lambda. So yes, you've got energy, you can use C in that respect, okay? Works. But obviously, again, if you're going to work out the energy of an electron that's moving, this you cannot use because it does not apply. The electron never travels at C. You just use your more standard E equals mv squared on 2. So often questions take you down a path where you need to figure out what the kinetic energy is of the electron to figure out some other thing that you need. So don't forget that the kinetic energy of the electron still applies, again, ignoring relativistic effects because that's not really part of the course in this bit, okay? All right, over here, you'll find this stuff here. The other version of questions that you get is, what is the wave nature? What is the particle nature of both of those objects, okay? Whether it's a photon or an electron, all right? So speed depends on the medium, so this is a nice little list that you can go through, which is good to have on a help sheet, which may actually be on that sort of generated help sheet that I made. Speed depends on the medium. That's a wave nature. 2 light beams can pass through each other without interacting. Okay, when light passes from one medium to another, refraction occurs. Light diffracts when traveling through narrow openings. Different colors correspond to different energies. So these are the properties of photons with similarities to waves or particles. You go through all of these, and they help you explain questions, all right? Okay, now there's only one more little thing that they've thrown into the course. Heisenberg's uncertainty principle, all right? So you've got this funky looking formula. Now, you've all heard that thing where they say there are some particles where you can say what their velocity is with great certainty, but you can't say where they are with any great certainty. Or you can say where this particle is with great certainty, but there's no way of knowing what its momentum or its velocity is with the same precision as you do its location. That's the Heisenberg's uncertainty principle, where you can't know the velocity and the position. Who's heard that?
You know the joke?
Oh, no? What's the joke?
Heisenberg's going along the freeway and the policeman pulls him over. Do you have any idea how fast you're going? So, you're going 10 km. Now I'm lost.
Because now he doesn't know where he is. Yeah, basically, yeah, absolutely. So there was another video that I showed. It's a Futurama one Okay. Heisenberg's uncertainty principle is based on this formula. Delta x, delta momentum has to be greater than or equal to this constant value, h over 4 lambda. Which h is this?
6.63.
Yes, it's 6.63. It involves momentum. It's 6.63. You never actually have to really calculate. What?
You mean pi or lambda?
That is pi. Oh, I'm sorry, what is that? H over 4 pi. What did I say? Lambda? Oh, you know when I watch these videos back, how many times I catch myself saying a stupid word in the wrong place and I'm like, oh my God, why am I doing that? I don't even know I'm doing it. Heisenberg's uncertainty principle. You can figure, now this is obviously what? A very, very small number. Okay, so this applies to very, very small objects. If you know where it is, okay, at some point, the knowledge of where this object is, its location with great precision, pushes this out because this is non-zero value. And this product needs to be bigger than or equal to this constant. This never changes, which means that as one goes up, the other one has to go down. And that's basically Heisenberg's uncertainty principle as a really very, very basic thing, okay?
So you can only know one, not the other.
Well, you can only know one with great precision, not the other. So now if you're watching the video, you have to watch the next video that I'm about to show, okay? All right, so this is a basic YouTube explanation of the idea of why one affects the other, and then there's a second video which is like, I think... So once you watch the video, you get a basic idea of, okay, what I take away from that video is, yes, a particle has a position, a wave doesn't really. The way you interact with one object is very different to the other object, and you can see why. Nice and easy, okay? But it was that marrying of lots of different waves, constructing or superposition with each other to make narrow regions of waves where you know where they are. All right, all that made sense, okay? Now, the next video I really, really like because it actually shows a practical effect of it where you can see. So it's the guy from Veritasium. I never remember his name. What's his name? Derek. That's right. It is. That's right. So Derek, right? He does this great video. Showing the effect.
And I'm firing it down toward...
So he's at Sydney University and he's going to actually demonstrate Heisenberg's uncertainty principle. I would love to make this little rig that he's got, which is so simple, but yeah. Okay. Have a look at this. So watch the next video. So what he's saying is, the way you look at delta x in the relationship is how wide the slit is. That is what delta x is. So that's your uncertainty. So if the slit is really, really wide, delta x is really big. The photon, or whatever object you're firing through there, could be here, it could be here, anyway. But if that slit was like really, really, really narrow and you're getting a beam through there, then you kind of know where it is. You know when that slit's really, really tight that, that those photons, you have very, very high certainty in where that photon is. It can't be anywhere left or right of that slit because it wouldn't have gotten through. It will only get through if it's like right there. Okay, and that's when you get to the limit that he described, Heisenberg's uncertainty limit, where now what happens is the momentum of these packets, he called it the x direction, but what he means now, this is the other thing, you've got to be very, very careful. In these questions, they will ask you, okay, what happens to the uncertainty in the momentum or the velocity? They often use them interchangeably, the momentum or velocity. Momentum and velocity are like, you know, intrinsically connected. So they use those words interchangeably. So doesn't matter. But it's not the velocity this way that changes, that becomes uncertain. It's the velocity this way that becomes uncertain, which would explain what you just saw. The dot on the screen gets really, really wide as it's going through the slit. So it's diffracting through the slit left and right, not in that direction. This is not a part of that's not the uncertainty they're talking about in that direction. It's only in the sideways direction. And in some questions, you will see a little key here, and they'll call that X and that Y. So then when you answer the question, oh, the uncertainty in the Y direction increases as the slit gets narrower and narrower, okay? Because that's what it said. You look for the key. Always look for what they've actually specified as Y and X direction, because that is it's a super easy question to answer. Lots of people get it wrong because maybe the 6 questions that they did in practice had X in that direction and Y in that direction, so they just ignored it and wrote it. But then they come up against the question in a SAC or an exam and they call that X and that Y. And that's all it takes to trap people. You know what I mean? Look for that first before you answer in what direction. So this here is, this slit width is delta X, all right? Slit width is delta X, okay? But the uncertainty in momentum is always sideways from that, okay? Not in the direction that is actually moving, all right? So that's where you can almost imagine it's like diffraction, okay? So that is the idea. That's all of it, I think, in a nutshell. Took way longer than I thought it would. But if we just get out of here and go back to this. All right, here, you've got the notes. Write this out, and you can see in Colin's notes, you've got 1909, G.I. Taylor carried out single slit experiment using light so feeble only one photon passed randomly through its slit time. Interference fringes is built up on the screen, even though photons could only... Okay, as the photon passes through the slit, delta X is the slit width. Its position is known with some uncertainty. Heisenberg says that this introduces some uncertainty delta P. So beam spreads out, which is why I like that Veritasium video, because it really shows it's something you can actually imagine and picture. So when you're doing questions, you go, remember, what was his name? Derek. Remember Derek? How many things like, and then bam, you've got the answer to the question, because the questions are not very complex because they haven't actually asked you to know very much about it. Let's have a look at a couple of questions. Okay. So again, the classic version. On the left, you've got electrons, which are not as fine, okay, still particles, it's still exhibiting their very strong particle nature. So what can you say about the wavelength of the electrons being used and the photons being used? What can you, of those in that picture? They're about the same. They have to be the same, okay? So if they've got the same wavelength, do they have the same energies or do they have the same momentum? Same momentum. Do they have the same energies as well?
Probably not.
No, probably not. And you can adjust the wavelength of the electrons, because obviously the wavelength of the electrons is coming from the momentum. The momentum is a product of this massive velocity, which means you can actually adjust those by making them faster or slower. All right, to change that pattern as well. So what they've done is they've actually fired the electrons at the appropriate speed, momentum, to get the appropriate wavelength. Okay, so don't imagine that all electrons fired at some random speed will always have that pattern. No, it's related to their momentum. Okay, all right. So that's 3 there. And question 4: light sometimes behaves as a particle and sometimes as a wave. Which one or more of the following properties does light sometimes show? Does it ever show mass? No, it never shows mass, okay? Does light show charge? No, okay? You never say light is positively charged or negatively charged. Like, that's never part of it, okay? Does it have energy? Well, yes, we get our energy from the sun.
Does that always?
This will be interesting. write the letters A, B, C of the following objects in order of the wavelength of their de Broglie wave's smallest wavelength first. A moving electron, an electron moving twice as fast as the one in A, and an alpha particle moving at the same speed as the electron. So what I would do is I would make sure I had this relationship in front of me, knowing that I have to go smallest wavelength, highest frequency, to longest wavelength, okay? So in this, a moving electron, and an electron moving twice as fast as the one in A. So A and B, which one's got a shorter wavelength? Sorry? B. B would have a shorter wavelength. So it's B first out of A, so it's B then A. And then where does C fit in? An alpha particle moving at the same speed as the electron in A.
That's 4 times the rate, right?
Yes. Oh, no, it's actually...
Oh, an electron.
Yeah, an electron. So it's like thousands of times more massive. So it should be way shorter. Yeah. Way shorter. So that puts C in first position. The shortest wavelength. Yes? CBA.